Hello everyone, welcome back to Networks class. So this is our second lecture, and last time we discussed some examples of networks problems. And then after those examples, we just did a little bit of administrative stuff looking at the class syllabus, and then we talked about Project Zero just to get you started on your projects for the quarter. And the plan for today is to begin by reviewing Big O notation and then review some basic properties of the most common data structures that we'll be using in class. So let's get started. So in terms of reviewing Big O notation, you've likely seen things like this before. So f of n is, or rather, g of n is big O of f of n. And what this means, or intuitively what you should be thinking that this means, is that this is like a less than or equal sign, except it's eventually and ignoring constants. So in particular, big O is a statement about growth. So the expression g of n is big O of f of n is saying that the function f is growing faster than the function g. So in addition to just this intuitive understanding, let's write down kind of some mathematical definitions for this. So here's kind of an easy definition, which is you just take a look at the limit as n goes to infinity of g of n over f of n, and that has to equal to some constant that's less than infinity. So just to give you an example of this, let's say that we're looking at if n is big O of n squared. So applying the easy definition, what we would do is we just take the limit as n goes to infinity of n over n squared, which is just equal to the limit as n goes to infinity of 1 over n, which is 0, and that's indeed a constant less than infinity. So yes, this is true. N is indeed big O of n squared, or intuitively, n squared grows bigger than n. So let's just take a look at one more example here. So is 5n, is that big O of n? So just by looking at the functions directly, you might think not, because 5n somehow looks bigger than n, but they actually grow at the same rate. So this less than or equal to sign here definitely does hold. So let's see why that is, just applying the simple definition. So if we take the limit as n goes to infinity of 5n over n, we get that that's equal to 5, and that's indeed a constant less than infinity. So yes, 5n is big O of n. And just to be totally exact, the exact definition of big O is the following, that there exists some constants n naught and c naught such that for n bigger than n naught, we have that g of n is less than or equal to c naught times f of n. And so our intuitive understanding in terms of eventually comes from the fact that we're only looking at n's that are bigger than n naught. And our intuitive understanding in terms of ignoring constants comes from the fact that we're allowed to multiply the function f by any constant that we want up here, and the statement would still be true. So that's the basic idea in terms of what big O means. And just to kind of get a complete picture of everything, let me just introduce you to a couple of other very common notations. So we won't see these very much in class, but it's worth mentioning them in case you happen to see them written somewhere so that you're not caught off guard. So if you see a statement like g of n is omega of f of n, what this means is this is really the exact same thing. Instead of being a less than or equal sign, it's a bigger than or equal sign. So it's saying that g of n is growing bigger than f of n. So really this statement is true if and only if f of n is O of g of n. So what I did here was I just swapped this direction of the inequality. So here it's the original less than or equal to sign that we saw at the beginning. So that's how you can say greater than or equal to. And of course, you can say something that's basically the equivalent of equal to, which is g of n is theta of f of n. So this means that the two functions grow exactly the same, and that's true if and only if both g of n is big O of f of n and f of n is big O of g of n. So both of those have to be true for the theta statement to hold. And let's just take a look at one simple example of that. So let's see, is 5n, is that theta of n? Well, we already saw that 5n was big O of n earlier, so that's definitely true. And then is n big O of 5n? You can just directly apply the limit definition that we had up here, and you'll see that it is indeed true, so that's also true, and so this statement over here is true. On the other hand, if you were to check if n is theta of n squared, this would not be true, because we have that n is O of n squared, but we don't have that n squared is O of n. So this is not true. And the way that we can see that is if we just apply the limit definition. So over here we want to check if n squared is big O of n. So that means we have to take the limit as n goes to infinity of n squared over n. And that's the limit as n goes to infinity of n. Which is infinity. So that's not a constant less than infinity. So this is not true here. So wrong. And so n is not theta of n squared. So that's the basic review of what big O means. But primarily we're going to use big O notation to evaluate the running times of the programs that we see in class. So let's kind of review some big O rules that will help us evaluate the running times of programs. So the first couple of basic rules are the following. So if I have a sequential program, so in other words, I have something that has a step 1 that, let's say, step 1 takes O of f of n time. And then I have a step 2. And let's say step 2 takes O of g of n time. Then to figure out what both of these steps together, how long that takes, I have to add the running times of the first step and the second step. So together, these would take O of f of n plus g of n time. And that really makes sense because in terms of running time, first you have to execute step 1, then you have to execute step 2. So let's take a look at the second rule, which is about loops. So suppose that I have a program that looks like this. So it's just a loop, and inside of the loop we do a step that takes, let's say, O of g of n time. And let's suppose that this loop repeats O of f of n time total. So in other words, we're going to go through this not only once, but we're going to go through it multiple times. And in fact, we're going to go through it f of n times. So how long does this thing take together? Well, this loop together takes O of f of n times g of n. So in other words, when I have a loop, I have to multiply the work inside of each step times the number of times that I repeat the loop overall. And this really makes sense. The way that you can think about it is you can just think about rolling out this loop. So if I rolled it out, if the loop repeated 3 times, what's going to happen is this step is going to get executed 3 times, and that really matches up with this sequential program rule that we saw at the beginning. So those are our two main rules about how to turn a program into some big O notation in terms of its running time. But we also have some simplification rules. So these rules help us take a big O expression and turn it into something more manageable and understandable. And there's really only 3 of these rules. So the first rule is that constant multiples disappear. So what I mean by this is if I have O of f of n plus f of n, just using your regular addition rules, you might say that this is O of f of 2n, or O of 2 times f of n. But this constant here doesn't matter, so we can just rewrite that as O of f of n. And that's because big O ignores constants, so you can just drop that 2, and we get just O of f of n at the end. So the second simplification rule is that smaller terms go away. So here's what I mean by that. Is basically the following. If I have O of small plus big, then that's just going to be equal to O of big. And in particular, what I mean by small and big here is that small has to be big O of big. So just to give you a very specific example, if I have O of n plus n squared, the bigger term here dominates. So I know that n is big O of n squared, so the sum of these two is just going to be O of n squared. So this rule just lets us know that if I know for a fact one of the 2 terms is going to be smaller, I can drop the smaller of the 2. And the third rule is also pretty direct, which is that if we don't know which term is bigger, keep both terms. So this is going to become important for us in class later because we're going to be looking at running times in multiple parameters. So not only n, but maybe another parameter m. So if you have something like big O of n plus m, and you don't know if n is bigger or m is bigger, you can't simplify that. You just have to leave it as it is. So let's just do one big example of computing the running time of a program to make sure that we understand everything. So let me just write down a big complicated program here, and then we can compute its running time. So here's a program. So for k from 1 to a, for L from 1 to B, and then let's say inside of these 2 for loops, we have a step taking O of n. And then outside of both of the for loops, we have another for loop. So here I have for k from 1 to a. And inside of this, I have a step that takes O of n time. Outside of this loop, I have a step taking O of n squared time. Then I have another very big set of for loops. So for k from 1 to n, for L from 1 to n, and for I from 1 to n. And inside here I have a step that takes O of 1 time. And then outside of all 3 for loops, I have something that, so here I have a step that takes, let's say, O of A, B, N time. So let's try to compute the running time of this big program. And to do this, we're just going to apply our multiplication and addition rules. So let's first compute the running time of this initial doubly nested for loop. So to do this, I have to know the running time of the inner step of this outer for loop. And so to do that, I can apply my multiplication rule here. So I have O of B times N for this inner for loop. So I multiplied the number of times that the loop is getting executed times the amount of work in each step to get O of B times N. And then I can apply again the loop multiplication rule to get the running time for the outer one, which would be O of A, B, N. So that tells me how long just this first loop runs. Similar reasoning tells me that this one runs in O of AN. This is a single step, so no multiplication required here. So for this triply nested for loop, we can work from the inside out again. So this is O of N, where I multiplied this one times this N, which was the number of times that the loop repeated. Then I get a O of N squared when I take the second loop into account, and then O of N cubed when I take all 3 of the for loops together. And then finally, I have this one step. It's just on its own over here. So now that I've figured out the running time of all of these for loops, I need to figure out the runtime of the program as a whole, which means I need to add up all of the running times here of all of the sequential steps. So the first step is to add the O of A, B, N that came from this doubly nested for loop. And then to that, I have to add the O of AN, which came from this for loop right here. Then I have to add the O of N squared, which came from this sequential step on its own, plus a O of N cubed, which came from this triply nested for loop right here. And then I have to add the O of ABN. So let's add all of these 3 together, or all of these terms together, and apply our simplification rule. So our first simplification rule tells me that if I have 2 terms that are the same, since constant don't matter, I can drop one. So that lets me drop this O of ABN because I have another O of ABN at the end of the expression here. Another simplification rule tells me that I can drop the smaller terms. So I know that O of N squared is smaller than O of N cubed, so I can drop this O of N squared. So now let's look at the 3 remaining terms and try to figure out if one is bigger than the other. Well, ABN is always bigger than AN if B is bigger than 1. So let's just assume that B is indeed bigger than 1, which means that we're going to be executing at least one of these B's. So that tells us that this O of A of N is smaller than O of ABN. So in total, the sum of all of these things is just O of N cubed plus ABN, applying our simplification rules. So that completes a brief overview of big O, or the important parts of big O that you'll need to know in class, which is roughly its meaning. It's a statement about growth and as parameters change, and then all of these simplification rules in terms of taking a program and turning it into the running time. So let's move to the second topic for today, which is basic data structures. So we'll review three basic data structures and their associated properties. So the first one that we'll take a look at is an array with n elements. So the basic questions that we want to answer here are the following. So the first question is, how long does it take to access the element in the ith spot? So in other words, I have an array and somebody comes along and tells me, give me the element in the 5th spot. How long would that take you? And the answer is constant time, so O of 1 time. And the reason for this is the following. So an array is a contiguous part of memory. So all of the spots in the array are right next to each other. So this would be the spot for 1, 2, 3, 4, 5, and 6. And to store the array, we basically have the initial start of the array here as a pointer. And when somebody comes and says, give me the 5th element of the array, what I can do is just add 5 to my current location, and that immediately takes me to the spot where the 5th element is. And so with just a single addition, I can return the 5th element of the array. So this is very fast, and it's because all of the elements of the array are located contiguously one after the other in memory. So let's answer the next question, which is how long to add an extra spot to the array. So in other words, I have here my array of size 6, and somebody comes along and says, well, 6 is not big enough. Can you make the array so that it contains 7 spots? And the answer to this is O of n time. And it's because of the following. So imagine that I have my array here. It currently has size 6, and it's in memory. But let's say that there's other stuff filling memory before and after the array. So I can't just add a spot right at the end and have everything work out well. So to add a 7th spot, what I have to do is find an entirely new place in memory, create 7 spots in there, 1, 2, 3, 4, 5, 6, 7. And then I have to copy over all of these elements. So 1, 2, 3 I have to copy over, 4, and so forth. So it's really this copying that gives us the O of n running time, because I have to copy each one of the original elements in the array to the new spot in memory. And the reason I have to do this is because I'm trying to maintain the property of arrays that everything is contiguous, one after each other in memory, which gives me that fast access time that we saw at the beginning. Okay, so let's move on with a couple of other questions about arrays. So the next one is how long to check if the number 5 is in the array. So to check if 5 is in the array, essentially you just have to go through the whole array looking in every box to see if 5 is in that box. So that's why this takes O of n time. But let me throw a small twist on that, which is what if the array is sorted? Then how quickly can I check if 5 is in the array? And the answer turns out to be O of log n. And the reason is because of something called binary search. So let's discuss how binary search works. So imagine that I have an array right here, and it's sorted. So this is a sorted array. And somebody tells me, is 5 in the array? Well, one thing I can do is I can jump right to the middle of the array right here and ask, is 5 bigger or smaller than this middle element? And suppose that I find out that 5 is bigger than the middle element, then that allows me to just cut off this entire bottom half of the array. I don't have to look there at all. And so with one look, I cut off half of the array. So with one look, we cut half of the array. So how long did this one look take? Well, just the single look took O of 1 time. Because the array is contiguous in memory. So looking at the middle here just takes me a single addition and an address jump. So it's very fast to look at this middle element. And so the number of times you have to divide n by 2 to get to 1 is log 2 of n. So the reason I say this is because how do we know that this algorithm will be done? So the algorithm is look in the middle, cut off half, look in the middle again, which maybe lets you cut off a different half, and keep looking in the middle. So with every look, I'm cutting half of the remaining array. And I'm basically completed when I get down to a single box, a single cell in the array. So the number of times that I have to look is basically log 2 of n. So that's why O of log 2 of n time to see if 5 is in a sorted array. Okay, so that completes the review of arrays, and let's look at our next data structure, which is linked lists. Now, a linked list is different than an array because its elements don't have to be in a contiguous part of memory. So element 1 is in some place and includes a pointer to tell you where element 2 is, which includes a pointer that shows you where element 3 is, which then points to element 4. So they're not next to each other, but you can kind of follow the chain from one element to another. So let's ask similar questions about linked lists that we asked about arrays just a short while ago. So how long to access the ith element? Well, unlike arrays, because in a linked list things aren't contiguous, to get to the 4th element, I actually have to follow the entire chain. I can't just immediately jump to the address of the 4th element. So in the worst case, that means that I might have to walk through the whole array. And so accessing the ith element in a linked list takes O of n time. So what about adding an extra spot? So how long to add an extra spot? Well, the answer here is O of 1 because things don't need to be contiguous. So if you want me to add a new spot to this linked list from 1 to 4, I can just do it like this. I just go to any other place of memory, create spot 0, make it point to 1, and I just created a new spot to the linked list. So adding an extra spot is very fast in a linked list. So what about how long to check if 5 is in the list? Well, you just have to walk through the whole list to check if 5 is in there, and so that's why this takes O of n. And what if the list is sorted? So if the list were sorted, that ended up helping us a lot in an array. But in a linked list, we can't do our neat binary search trick over here because you can't do this jump to the middle of the linked list to see if 5 is bigger than or smaller than. So even if the list is sorted, it still takes you O of n time to check if 5 is in the list, because our nice trick of binary search just doesn't apply here because we can't do these quick jumps to the middle. So let's continue with our final data structure for today, which is a hash table. So hash tables are probably the most widely used data structure, and that's because they really have, in some sense, the best of both worlds between arrays and linked lists. So let me just tell you a little bit about how to think about what a hash table is, and then we can go into its properties. So think of this as an array where the index can be anything. So here's what I mean by that. So a hash table, it stores key value pairs. So just to have an example of this, here's maybe some keys, A, B, 17, the word school, pretty much anything. And then each of these keys has an associated value. So maybe A is associated with the value of 2, B is associated with the value of 5, 17 is associated with the value of 1, and school is associated with the value of 10. And so a hash table gives you very fast access given a particular key to its associated value. So the way that a hash table does this is that it takes the key and it passes it through something called a hash function. And this hash function basically produces a number that you can think of as an address in memory. And this hash function works really fast in O of 1 time. So in other words, when you come to somebody with a hash table and you ask them, what's the value for school? What they're going to do is they're going to take the word school, pass it through this hash function, and it's going to give them a number. And then they can just look at the resulting number and the appropriate address in memory to see what the value of school is and return the value 10 if they're holding this particular hash table. So let's look at some of the properties associated with hash tables. So how long to access